Hi everyone, and welcome to our review video for ECU 2111. This review video will be focused on systems. So in the past review video, we reviewed some of the main ideas about signals from the course, and now we'll see how these help us to understand systems. Okay, so the plan is to remind ourselves what is a system, to understand basic properties of systems. Okay, so this is largely terminology. And then to look at kind of the key question that we focused on throughout the course, which is how to relate the input and output of a linear time invariant system. Okay. So linear time invariant was one of the key properties that we studied in the course. Okay, and we'll remind ourselves what that means in a second. Right, but in some sense, most of what we've been doing has been related to this question of, in various ways, how do you relate the input signal and the output signal of a linear time invariant system? Okay, so that's going to be the main plan. So let's get started with systems and their properties. Okay, so a system is something that takes in a signal and produces a signal. We can describe systems in various ways. Okay, they're much more complicated to describe than signals. Okay, but still in this review, we'll review some of the ways in which we describe a system. But often we just draw systems in this kind of block diagram way. And think of them as an abstract black box that does something to a signal. We saw throughout the unit a number of different properties of systems. Okay, these allow us to sort of classify systems in different ways. And in particular, the main property we're going to focus on in this unit is being linear and time invariant. That's the key property, the most important one. There are a bunch of other properties that we looked at. So, we looked at these two separately. So there's linear systems. Okay, these obey sort of superposition, if you like, and scaling. Okay, so if you scale the input signal and you put it through the system, the corresponding output signal is scaled. If you add up two inputs and put them through the system, it's the same as putting the inputs through the system separately, and then adding up the outputs. Okay, we also had time invariance. And that meant if you delay the input signal and put it through the system, that's the same as putting the input signal through the system and then delaying the output. Okay. We also had causality, so being the property of being causal. So this means that the output at the current time does not depend on the input at future times. We had a special case of causal, which is memoryless, which means that the output at the current time depends only on the input at the current time. Okay, so we had these key properties of systems. The other key property we had of systems was being Vibrostable. Okay, so Vibro means bounded input, bounded output, stable. Okay, so what does that mean? That whenever the input is bounded, the output is also bounded. Okay, so these were some of the key properties of systems that we studied. Right, in particular, the main class of systems we focused on are linear time invariant systems, and we were interested in whether, in understanding various things about linear time invariant systems. We looked at these properties in the context of linear time invariant systems, so causality, memorylessness, being Vibrostable. We also, and in particular the focus, is really understanding, again, this question. For a linear time invariant system, how do I relate the input and output signals? Okay, so before we study that question about inputs and outputs, what I want to do is remind you about different representations we had of linear time invariant systems in particular. Okay, because these are really the focus of this unit. Okay, so what different descriptions did we have? We had the impulse response. This is denoted H, and it's the output of the system when the input is the unit impulse. Okay, and that definition makes sense both in continuous time and discrete time. Okay, that's one representation, and this is kind of a time domain representation. All right, so just to be very clear, this representation of the system is in fact a signal. Okay, so we represent this system by the signal H. Okay, but that signal H contains, knows everything about the system, right? So this is slightly confusing. We represent the system via the signal H, which is the output of the system, when the input is this special signal, the unit impulse. Okay, so that's impulse response. Then we had frequency response, okay? And this is only for Vibrostable systems. Okay, so what's the frequency response? This is usually denoted by capital H, and it is defined by the following. So if the input to an LTI system is this unit complex exponential, okay, at frequency omega, then the output is some complex number times the input. Okay, so these signals are very special. They're signals that when you put them through the system just get scaled by a complex number, and this is the frequency response at frequency omega. Okay, so this number will change as you change omega, and if you collect together all these numbers, you get the frequency response. And so an important fact is that the frequency response is the Fourier transform of the impulse response, and this is true in continuous time and in discrete time. Okay, so in continuous time you use the continuous time Fourier transform. In discrete time you use the discrete time Fourier transform. Okay, and so in this definition of frequency response I've written it in continuous time here, but if I replace all the t's with n's and use square brackets, and I think about the discrete time unit complex exponential input, I get exactly the same relationship in discrete time. Okay, so that was the frequency response. And the other key representation of a signal we had, of a system we had, is the transfer function. Okay, and this is not just for Vibrostable systems, so this makes sense as transfer function for all LTI systems. So these are always for LTI systems, everything in this slide. Okay, and this is often denoted H hat. Okay, and so again, what's the idea? If the input, again, I'm going to write it, this is only in the continuous time setting, what I'm going to say now, to a CT LTI system is now a general complex exponential, all right? Then the output is y of t equals h hat transfer function e to the st. Okay, and this is the transfer function at some complex number s. Okay, and in fact s should be not just complex, but really for this to make sense, we need s in the region of convergence of the Laplace transform of the impulse response. So what's the corresponding fact that I just hinted at? The transfer function is the Laplace transform of the impulse response. So these are our three main representations of linear time invariant systems. We've got the impulse response, which is kind of a time domain representation. Then we've got this true frequency domain representation for stable systems. That's the frequency response. So impulse response and frequency response we've discussed for both continuous time and discrete time. And then we've got the transfer function, which is which applies not just for Vibrostable systems, but for essentially all LTI systems. And this we've only discussed in continuous time. Okay, and so the relationships between these, let's just summarize those relationships. Okay, I've got the impulse response. Okay, and then there's the Fourier transform, gives me the frequency response. Okay, and the Laplace transform in continuous time gives the transfer function. And the other connection is this one. Okay, so the transfer function and the frequency response are closely related what's the statement is that if the system, this is always for an LTI system right now, is Vibrostable, then the transfer function at j omega is equal to the frequency response at omega. Okay, so this is that gives me this last connection. Okay, and so that's how these relationships, the relationships between these three representations of our system. Okay, now we have these representations of our system, we can look at our properties and try to see how do I test for my different properties, okay, from the point of view of these different descriptions of the system. So we had being causal. Causal is something that I can see from the impulse response. First, let's discuss how these appear in the impulse response. Okay, so system is causal if the impulse response is 0 for all negative time, and the same in discrete time. Okay, a system is memoryless if actually the impulse response is just some multiple of the unit impulse. It's Vibrostable if the impulse response is absolutely integrable in continuous time and absolutely summable in discrete time. Okay, and we've got one property I didn't mention before, which is in discrete time we think about having finite impulse response or infinite impulse response, and these are dependent on whether h has finite duration or not. All right, so these are some properties that we can directly see whether they hold or not from the impulse response. Okay, so we can also see in the continuous time case some of relationships to the transfer function. Okay, so we have that the causal, a system is causal implies that the region of convergence of the impulse response is a region to the right of some vertical line in the complex plane. Okay, so that's something, if you know the system's causal, you know the region of convergence has to be this kind of right-sided region. Okay. If you know the system's memoryless, that happens if and only if the transfer function is in fact just a constant. System's Vibrostable if and only if the region of convergence of the impulse response contains the imaginary axis. Okay, because that implies absolute integrability for the impulse response. And we also have, I suppose, that no, then we don't have an analog for finite impulse response and infinite impulse response in the transfer function setting, because those are discrete time properties and we haven't discussed the discrete time analog of the transfer function. So what have we seen so far? We've discussed systems and some of their basic properties. What I want to do is mention sort of the key examples of linear time invariant systems. So in discrete time, these are essentially a gain system, okay, a delay system, addition, so summers, okay, and essentially compositions of these. And so overall what you end up getting are systems defined by difference equations. So these are things with input x, output y, and we have relationships of the form the output and the previous, say, capital N outputs are related to the input and, say, the previous m inputs via some kind of difference equation. It's possibly recursive, so we call it recursive if these terms are present in the description. Otherwise, it's not recursive. Okay, and in the non-recursive case, you'll get a finite impulse response system. And in the recursive case, you'll tend to get an infinite impulse response system. Also, some care needs to be taken in the recursive case. Okay, we only get an LTI system if the sort of, let me call it the initial conditions, it's not quite. So if the system is subject to the condition of initial rest. Okay, so this condition of initial rest means that intuitively that while the input is 0, the output will be 0. Okay, so these are, in the discrete time case, this is the typical typical way in which we think about LTI systems, either as non-recursive difference equations or recursive difference equations with this condition of initial rest. Okay, in continuous time, our basic system blocks are again the gain block, the delay block, addition blocks, but now we also have derivative and integral blocks. Okay, we can build more systems by composing these, and in particular what you end up with is that many, but not all, so many continuous time LTI systems can be defined by differential equations. In particular, these are the ones that don't involve delays, but just involve gains, additions, and derivatives or integrals. Okay, so in general you have this kind of form. Okay, and again you have this kind of either recursive or non-recursive setting, and these will be LTI if the system is subject to the condition of initial rest. All right, so these are difference equations and differential equations, very common standard formats for linear time invariant systems, as long as we have this condition of initial rest. Okay, and so for these difference and differential equations, it's important for you to know how to go between the difference equation and the frequency response. So how to get the frequency response of these. And in the continuous time case, how also to get the transfer function. Okay, so you can go from this concrete description in terms of a difference or differential equation into our more abstract descriptions in terms of frequency response and transfer function, and then potentially from those you could invert and get the impulse response, so we can get all of our descriptions of linear time invariant systems. Okay, so what's the key other issue, and really what's been the focus in many ways of the unit, is to understand the input-output relationships for linear time invariant systems. Okay, so the first such relationship we saw is the convolution formula. Okay, so we have that in discrete time, so the output at time n is the convolution of the input and the impulse response. Okay, what does this mean? This is defined by this convolution sum. Okay, which you can also write the arguments the other way. Some problems it's easier to think about this formulation, and other problems it's easier to think about this formulation. Okay, so that's a formula that relates the input and the output and the impulse response, and here everything is in time domain. We also have a continuous time version of this, in which the sum is replaced by an integral, and again you can switch the order for whichever one is more convenient for what you're doing. Okay. All right, so that's the sort of time domain input-output formula. And then we have our kind of frequency domain formulas. Okay, so in continuous time, this is for now for Vibrostable systems. Okay, so we have that the Fourier transform of the output is equal to the frequency response times the input. And that same formula holds in discrete time. It's just that instead of the continuous time Fourier transform, you use the discrete time Fourier transform. Okay? All right, and so then finally the last version is kind of from the Laplace transform point of view, so we only studied this in continuous time, and we get that the Laplace transform of the output is the transfer function times the Laplace transform of the input. Okay? And so one thing that's very convenient about particularly the last two formulas is that, well, they're easy to apply, you just multiply, but also you can invert them. And so, for example, if you know the frequency response of the input and the output, you can find, if you know the Fourier transform of the input and the output, you can divide them to get a formula for the frequency response. And similarly for the transfer function. Okay, so this is a very, very useful thing to do. Okay, so this allows us, if we're given two pieces of data, the impulse response and the input, or the impulse response and the output, to find the third piece of data by moving to one of these frequency domain representations, okay, and using this relationship that the output is the product, the Fourier transform of the output is the product of the frequency response and the Fourier transform of the input, or the Laplace transform of the output is the transfer function times the Laplace transform of the input. Okay, and the key difference between the frequency domain version and the Laplace transform version in continuous time is that the frequency domain version only works for Vibrostable systems, whereas the Laplace transform version works for essentially all systems. Okay, so there's one setting in which we have not described this. We've done time domain, we've done frequency domain, but this is frequency domain with aperiodic inputs. Okay, so what happens for periodic inputs and Vibrostable systems? Okay, so here we have, if you have a periodic input, so we'll do the continuous time version first, then the input has some period t0 and some frequency omega naught. So the input has a Fourier series decomposition. Okay, and then it turns out that and so does the output. So the output is also periodic with period t0, and so the output also has a Fourier series decomposition. And you might ask how they're related, and how they're related is that the kth Fourier series coefficients on the output is the frequency response at frequency k omega naught times the kth Fourier series coefficient of the input. Okay, so that's the key relationship for periodic inputs in continuous time. In discrete time, the story is very similar. You have a periodic input with some period n0. So the input has a discrete time Fourier series expansion. Turns out the output is also periodic, and it also has a Fourier series expansion, and these are related by exactly the same formula, okay, where this is the frequency response in both cases, but one, is, for example, the continuous time Fourier transform, of the impulse response, and here I have the discrete time Fourier transform of the impulse response. Okay, so this is the situation for periodic signals. So what have we seen? We've seen an input-output formula in the time domain by convolution. We've seen input-output formulas for aperiodic inputs and Vibrostable systems via the Fourier transform. We've seen an input-output formula for periodic inputs and Vibrostable systems via Fourier series coefficients that relates the Fourier series coefficients of the input and the output, and again uses the frequency response. And we've seen an input-output formula for aperiodic inputs and not necessarily Vibrostable systems in continuous time using the Laplace transform of the input and the output and relating those to the transfer function. All right, so to summarize, what have we seen? We've seen signal systems. Okay, and in particular we've focused on LTI systems. We've seen that they've got a bunch of properties. Okay, and we can test for these by looking at the impulse response and for some of them the transfer function. We also looked at particular, I'll call them examples, but they're really pretty much everything coming from difference equations and differential equations. We saw different representations of our systems via the impulse response, the frequency response, and that's for Vibrostable systems, and the transfer function, and that's for continuous time only. All right, and we also saw input-output formulas. Okay, and these were based on convolution, based on Fourier transforms in the Vibrostable setting, based on Fourier series plus the frequency response, in the Vibrostable periodic setting, and then based on the transfer function and the Laplace transform in the aperiodic general continuous time setting. Okay, thanks very much.